right, so welcome everyone. I hope you still have energy, but we do still have energy, even though it's 5 p.m. in European time and 6 p.m. in Turkey. So today we had already very great sessions, so I'm sure this session also will be great. So we are gonna have today's last session in just 3 minutes. So I promise I will not talk too much and I will pass the stage to Krystian as soon as possible. Okay, so today, again, another very special guest. So my former colleague, forever friend, Krystian Zielinski. So he's working at the moment as a data scientist in Invicta, and he's doing great things around biostatistics and deep neural networks. And yeah, I had pleasure to work with him and we did very cool stuff together. So I think I will be passing the ball to you, Krystian, and stage is yours. So maybe before you start, just a few reminders for our participants. So please feel free to ask your questions. So during the speech, your mics will be closed. But after the speech, after Krystian finishes his speech, so there will be Q&A session on the way. So please don't hesitate to drop your question to the chat. And so Krystian, also feel free to pick them up or leave them to the end. So it's up to you. Let's get it started then. So Krystian, stage is yours.
Thank you, Olgun. Hello, everyone. My name is Krystian. I think Olgun already introduced me, so I won't talk too much about the background. We were working together on the financial crime. Right now, I'm working in the medicine field, but still as a data scientist. So today, I would like to show you how to use train neural networks in R. So let me just very quickly share my screen. I will explain how you can get the code that we will be using today. I created a repository on a GitHub for today's session. So I will drop it in the Zoom. Okay, I'm not sure how to open the chat. Okay, so here's the link for this repository. For this today's session, I think you will be mostly interested in the notebook file. So YR Turkey 2022 webinar. So if you right-click on it and save the file as, you will just be able to save the single file onto your PC. And after that, please put it into the drive and open it with Google Colab. Don't worry, it's still R Colab, not Python version, so it should work. If you are interested more into using the deep learning in RStudio, you can clone the whole repository, but I would suggest to do it after the session. So in prepare.env, you have the instructions how to install necessary packages. And then in lib folder, you have all of the R files necessary to run the script. But as for today, I think it will be the easiest to just download the notebook, and we will be able to together run the code and go through it. If you are not able to download it from GitHub, you can also just use the link because I made it shareable. So those are the two links that you will be mostly interested in. Okay, so for today's session, I would like to just introduce you to the deep learning, because the whole area of deep learning, as you may already know, it's deep. So it's not a topic for 1.5 hours of discussion. But today we will definitely learn how to create a deep neural network in R. We will learn how it works. We will run through some basic examples, so the regression issues and binary classification, multi-class classification. We will very briefly touch upon the explainability of deep neural network with package dialects. And then I will show how to compare the performance of different models using actually the dialects package that have different parameters. So that's basically the whole scope of the of today's session. As you may see, this is a Colab notebook, but I promised the deep learning in R, so you can see that it is an R version of the notebook. You should start with installing the necessary packages, so the Keras, Dialects, and Plot3D. Just a quick note, in Google Colab R version, Plotly is not working, so that's why I use the Plot3D for the visualization, but in those R files in the repository, instead of Plot3D, there are Plotly visualizations. Okay, so I installed those packages already. It may take like 2 minutes, so don't worry if it takes a bit time. It's exactly 2 minutes for me. Yeah, after they are installed and libraries are loaded, we will be good to go. To save some time and use it more into to explain the code, I created a couple of functions to generate the fake data and some utils functions. So I won't talk about them much because it doesn't make much sense. Those are just the functions to generate the data. So let's very briefly start with the introduction to deep learning and how it actually works. I don't want to make this webinar too theoretical, but I just hope that we will have the understanding on how the deep learning works and what factors actually affect the whole training process, because I think this is a part that's very often missing from the understanding of the whole topic. So this is an example of a two-layer neural network. Of course, it's deep learning, so we can have more hidden layers, but if you are able to understand the two-layer network, I think you are able to understand like n-layer network. It won't be so much different. So what we have, basically, we start with input data, as in any other algorithm, and the input data is passed to a first layer. So in first layer, here we have just one neuron, but if there would be more neurons, we will have just more dots here. So how the neuron works? The input data is multiplied by the first weight, and then if we are using bias, it is added. Bias can be also equal to 0, so then we don't have this problem. The activation function is being applied for this result of this calculation. Yeah, and that's the value of first layer. So then the result of the activation function is being passed to a next layer. And again, it's multiplied by the weight, the bias is being added, we are applying the second activation function, and it's passed to next step. So if it's last layer, this is basically the output of our model, so our prediction, so y hat. And this process of passing the data through the neural network is being called feed-forward. So we have the prediction, we have the real value, and of course we can calculate how much the neural network actually missed. So what's our error? What's the value of the cost function of neural network? So that was actually easy because we just passed the data through the neural network. But the whole trick is hidden here. So in the backpropagation. So how the neural network actually works. Well, it's not a mistake that it's called a neural network. So it works basically as, let's say, artificial humans. It learns as us. So it learns by making mistakes and then adjusting its weights on those mistakes value. Yeah, there are a lot of calculations. I won't go through that because it doesn't make any sense to explain why those values are the way as they are explained here. I just want you to know what values actually are affecting the adjustment of the weights and adjustments of those biases, because that's what we are interested in. Yeah. So in the example of the weight of the last activation function, what's important? So basically the input that goes here, the derivative of the cost function, and the derivative of activation function of this layer. So what it means, not only the activation functions that we are using are important, but also we have to bear in mind that in the backpropagation process, the derivatives of those functions are extremely important. So yeah, make sure that you're understanding correctly this fact, because I'm sure that everyone knows, as for now, how the linear function looks like, how the sigmoid function looks like, but also bear in mind that you have to know how the derivative of those functions looks like in each point, because this is the value that's actually being passed in the backpropagation process. So the weight of the first layer in this example, so the input data is important, and also the same values as in the adjustment of the second weight and value of activation of first layer. So basically I colored it. So for the adjustment of W2, the blue dots are important. So in adjustment of this yellowish W1, blue and yellow values are important. Where just bear in mind that's not the actual value of those activation functions, but the derivatives are the ones that we are interested in. For biases, basically the same, but we are not interested in the input data, so what's being passed. Yeah, so from this, I want you to remember what is actually important in the learning process. So the value of the cost functions, also derivative, but basically the value of the cost function, so how much we miss the actual real value, the derivatives of the activation functions, and the input data. That's basically it. Okay, all right. So with that being said, I think we are ready to start the actual programming. So how to translate this into R code. For today's session, I want you to get to know the Keras package. I think that Keras and the TensorFlow are being mostly known from their Python implementation, but there is an R version of that. So it's very similar, the R version and the Python version. That's why I think it's the easiest package to, get rolling in R. So step by step, if you want to initiate the model, you just call the Keras model sequential, which has like a lot of parameters to adjust. You can check the website. I've passed links there with all of the parameters that you can pass into the model, because of course that's not all of it. This is like a minimal version of deep learning. So then if the model is initiated, we have to create its structure. So we basically have to add our layers. So the first, what's layer combined of? So we have to pass the number of units, so the number of neurons in the layer. We have to pass the activation function. By default, it's linear, but you are rather changing that. So all of the activation functions you can check in the documentation. Yeah. And many other arguments. Again, I won't go through all of them, but you can definitely check the regularizers. There are a couple of arguments being called regularizers that are basically preventing the overfitting. So, FYI, that's probably the ones that you will be also interested in. Yeah, and the first layer is a bit different than the others because you have to pass also the input shape, so the number of the dimensionality of the input data. And then you're just adding more layers. So you can also add the dropout layer. So for now, you should know that it also helps to prevent the overfitting. Basically, a part of the neurons won't be connected with each other. So that's the idea behind it. And you're adding the hidden layers, as many as you want, as many as they are needed. And then the last layer is also a bit different because you want to make sure that the number of units, the number of neurons is the same as the dimensionality of predicted value. So for regression, it's probably 1 neuron. For multi-class classification, it's n neurons, and so on and so on. And the activation functions also for the last layer, you should make sure that it's corresponding to the issue that you are wanting to solve. So basically, the golden rule, you can say that linear for regression models, sigmoid for a binary classification, and softmax for multi-class classification. Yeah, so we have the model. We know the structure right now because we created it. The last steps are compiling the model. So, passing the loss function. Again, many of different losses functions you can check in the documentation. The optimizer. So basically, optimizer is an algorithm, the method on which the deep neural network works. It adjusts its wages. And also, like the argument of the optimizer is learning rate. So it's basically a speed of learning of the neural network, the ratio of updating weights and biases. And the last argument, the metrics. Those are the values you would like to see how they are updating in each iteration of training the model. When the model is compiled, you can just feed it with the data, and this is the part that's actually being called training. So you pass the trained data set, the labels of the training data set, number of iterations, validation split if you want to split the data into the train and validation subset. Callbacks, many of callbacks. Today we will cover just early stopping, but make sure that you go through all of them because this is kind of important. Class weight, yeah, this is for unbalanced data classification, might be useful. Sample weight, again, might be useful for unbalanced data. So that's basically it. So as you can see, there are just a couple of golden rules that you have to keep to create a model, and in about, I don't know, like 30 lines of code, you have the whole deep neural network created, compiled, and trained. So I would say it's very easy in R right now. Okay, so let's jump into the simple examples. I created a function to split the data into train and test subsets, just to avoid like copy pasting a lot of lines of code. So let's create a simple linear regression problem. So as you can see, this is like a simple linear function which we would like to feed our model, feed this data into our model. So let's split the data and create a model. As you can see, this model has only one unit and only one layer. So it is Keras model, but it's not deep learning yet, because deep learning means like we have a lot of more than one, at least, layer in our model. But this is simple linear problem. So this should work. This should be enough to train the model on our data. We will use mean squared error as our loss function and simple stochastic gradient descent as the optimizer. Let's feed the model with our data and plot its history. As you can see, only 10 iterations there, but in those 10 iterations, we can see that the loss function, the value of loss function is being reduced like around six times. Okay, so let's check the predictions. To predict the value, you just use the predict method with the test subset without our label, of course. Yeah, so in the visualization, you can see in the blue color the real value, in the red color the predicted value. So as you can see, we didn't predict our values. Like we weren't even close, to be fair, to predict the proper values. But maybe it's due to the fact that the whole model was trained only in 10 iterations. So right now, the task for you to train the model in 100 iterations and see if our predictions meet the reality in 100 iterations. I will give you like half a minute, as it shouldn't take too much time. Just check the predictions after you train the model in 100 iterations. So bear in mind that the model was actually trained already. So if you want to recreate it, you should start with this cell, running the code in this cell. Then you will overwrite the model with a new one that's with fresh values of the weights. Okay, so let's train it and plot the history. Okay, as you can see, right now we are very close to a 0 value. So our predictions should also be much closer to real values. And that's actually the case. The real values are not so far away from our prediction, but as you can see, and you should get used to that in our regression problems, at least. So the model has some problems on the very edges of our data set. So bear in mind that this is still a regression problem, a regression task. So the model will be most probably the most efficient in the middle of the pack, and the highest errors should be expected on the edges of our predictions. Yeah. But we are fairly close to actual values. Okay, but that was easy. Come on, like it's a linear problem, so we know how to solve it. That's not the reason why we are using the deep learning. So let's go with something harder, something tougher to recreate. So everyone knows the sinusoid, how it looks, and why it looks like that. It's natural for us, of course, because we know the shape of it, but for the regression, from the regression point of view, it's actually not that simple, because you would have to recreate it with a combination of linear function, which might not be the easiest task for the neural network. But let's try. So we will start with this time actual deep neural network. So we have 1, 2, 3, 4, 5 layers in our model. We are using the ReLU activation function in the hidden layers, and as the last layer, we are using the linear, as it is a regression task. Okay, I think maybe right now it's a good moment to talk a little bit about what are the activation functions. They should be used like by default. So by default, we are most often using the ReLU functions in our hidden layers because of the simplicity of it. So it also like the computation times of ReLU is very simple, but also bear in mind what is the ReLU derivative. So it's either 0 or 1, but it's 0 only when the input data is also it's negative. So that's the rule for the ReLU. We usually won't be using the sigmoid function in our hidden layer. So why is that? Again, let's just imagine the sigmoid function. So it looks like that, basically. And the values are from 0 to 1. So basically, what's the problem with the sigmoid function? The value, the derivative of sigmoid at the edges of it, so on the left and right hand side of this function, like it's basically a constant here because it goes up to 1 and up to 0, and the derivative of the function that's very close to constant will be a very close to 0. That's why we might have a problem with actual starting the training there. Because the derivatives will be close to zero. And as you can remember, in backpropagation, we are multiplying here. So if one value is very close to zero, then the whole adjustment of the weight will be close to zero. And that's the problem with sigmoid function. Also, it's very painful when we have like a lot of hidden layers. I'm sure you've already heard the term vanishing gradient. So that's basically it. The information from the cost function basically disappears the deeper we go into our model. So that's why we can use, of course, there are some case uses of it, but by default, we would rather use the ReLU and the similar functions to ReLU in the hidden layers rather than the sigmoid. All right, and we are compiling the model. So let's go back to our problem, the regression problem. Again, we are compiling it with the same values as before, so mean squared error, SGD, and so on. And let's train the model for 50 iterations, 50 epochs. Yeah, and we can see from those 50 iterations that the model in the first phase kind of was training. After that, the validation error skyrocketed, we can say. So the predicted values should be quite far away from the real values, and that's the problem. We can see that the model kind of started to train, but is still very far away from the actual values. So what we can see, what we can do right now, of course, we can increase the iterations, but the problem might be the computation time. Usually for bigger data sets, we would rather change the training parameters than increasing the iterations, because this computation power, it takes time. So what are our options? We can increase the learning rate, of course, to speed up the training, and also change the optimizer. So yeah, it's once again hour and a half, so I won't be able to go through all of the aspects of deep learning, but optimizer really matters. And especially Adam is known for its quite fast approach to a minimum value of the loss function. So we can check those two. So first of all, you can increase the learning rate. You can do it yourself at home. Right now, it's as the default value of stochastic gradient descent. You can increase it to, let's say, 0.05. And then after that, change the optimizer to Adam. Okay, so let's do it together, maybe, and check how the training process actually, how it affected the training process. Yeah. So increasing the learning rate, still kind of questionable. We can see from predicted value that model is fitted better to the data, even though the error is still high. It at least it understands the half of the data, we can say. So I'm pretty sure if we would increase the epochs, it would solve the issue. But we can also just change the optimizer. So instead of SGD, use the Adam. But the Adam optimizer has a lower default learning rate, so it's 0.001. So let's use, as for now, the learning rate. So we can call it overfitting or not. I think we can definitely call it overfitting from this plot, because we can see that the error on the validation data and the training data differs. I wouldn't be so hot on calling this overfitting only looking at that, just because maybe, but just maybe, the error on the training data is like the predictions on the training data wouldn't be a sinusoid. I think we can check it very quickly. So instead of test, we can use the train subset. So the model still misses. So, okay, but this is actually a very good question, whether or not we can call it overfitting. I think technically yes, because the model looks like it's overfit, but on the other hand, we know the prediction data, so we know that there's still a way to increase the prediction, the accuracy of this prediction. So as in this example, like changing the optimizer. So let's create the model with Adam and train it. Yeah, you can see that the error values look much different. And right now, the data is way closer, like our predictions are way closer to a real values. There's still problem with this subset, but again, I think more iterations would solve it, basically. Yeah, so technically we could say that that was overfitting, but in a reality, if we would allow the model for more iteration, the error on the training subset and the test subset, validation subset, would go closer. So yeah, that's kind of like double-edged sword. So the question, how can we decide optimum number of training iterations? Yeah, rule of thumb, I would say it depends. Obviously, it depends on the number of features in our data set, because the more features, the more complicated the model will be, obviously. So, so for the more complicated data sets, we would rather use more iterations, a bit more complicated architectures, of course, and maybe even a lower learning rate, and let the model train for a longer time with smaller learning rate, and you know, smoothly go to an optimal value. But very often we don't have to decide on the optimum number of training iteration. That's what early stopping is made for, and I think I will show it in next example. So let me just go through it, and I will explain what early stopping means and why it avoids the problem of deciding on optimal number of iterations. So in the third example, we have a strange looking data set. So this is a three-dimensional data set. As you can see, the X and Y values, this is basically a circle with some noise. But our goal will be to predict the Z values, which is also the color of the model. Yeah, So that's a strange looking data set. To be fair, a fun fact, I tried to generate a bit different data set, and by mistake, it looks like that. But then I saw it and I thought to myself that, well, this is kind of strange. Maybe it's even more interesting to predict this one. So that's why I just left it right like that. So again, let's split the data. Let's create a model. A very similar model to our previous example with 4 layers. Let's use the Adam optimizer and the early stopping. So why we don't always have to think about the maximum number of iterations. So the early stopping is a callback that in the training process basically looks at the monitored value. Probably you will use the validation loss, but there are different versions. You can use here loss or metric values for the monitor, and it checks whether or not the monitored value decreased in this example or increased, but changed by a given delta in the given number of iterations. So this example, we will be patient for 30 iterations. If that's not the case, so if the model didn't decrease the error, so in this example, decrease the loss for 30 iterations, the whole training process will just stop, and we will restore the best weights of model. And why is that so important? So let's again take a look at this example. So we can see here. So this is the minimum that the minimal value of loss that the model had on the validation subset. But the training process went on, and let's imagine that we have early stopping, and it stopped right there. So we went through 50 iterations, but clearly, if we would stop at 35, we would have a model with lower error. So most probably, this model is better. So we would rather use the weights at the 35th iteration. So we will restore the weights of the model at this checkpoint. That's why it's important. Okay, so let's create an early stop and train the model for 100 iterations. As you can see, I passed the early stop into the callbacks argument. A callbacks is a list, so you have make sure that you're using the list there. When we are visualizing the training process, you can see that it stopped at around 55 iterations, something like that. Even though we said train for 100. Because the algorithm didn't see much sense in later iterations, we can see that the error on the validation subset is basically the same. Okay, so let's predict the values and visualize the real data together with the predicted data. Okay, I hope that it doesn't take so long for you, because it should be faster. So probably there might be some temporary issues with my connection. Okay, so we can see that the real values and the predicted values are basically the same. They look the same. So model solved the problem without much trouble. Later on, after after all of the examples, you can check with different optimizer if it's the same. Probably not. If I'm saying that, you should definitely check it out. So it also shows that the optimizer stochastic gradient descent might be a bit slower than the other. Okay, explainability. So for today's session, I will use the Dalex package. Like it's the best one I found yet, both for R and Python. It's very diverse. You can use it on very different types of models, and it also supports the Keras models. That's why, like, it's just the best. You should definitely use it. I don't see any reason why you shouldn't. Like, really, it's just great. So, couple of visualizations there. Couple of visualizations for the explainability. The Dalex, supports a lot of different types of plots for explainable AI. I won't go through all of them. Again, not enough time, but you should definitely check them out. So the first one I'm usually checking is the reverse commutative distribution of the absolute value of residual. So basically, how many percent of the observation had a given value of residual, absolute value of residual. So it's basically an error that model makes, prediction error, or lower. So we can see that in this example, 50% of the observation had error around 0.01, I would say, something like that, or lower. And only 10% of, maybe it will be easier. So only around 2.5% of the observations had the error at 0.04 or bigger residuals. So it shows the distribution of the errors. This is very important, especially for the regression, because in an ideal world, we would like to have the model to have the residuals around 0 without any outlying values. So if we would see the behavior like that, definitely we should check out those observations where the residual is way higher than the other ones, because those are some outliers. Maybe those are some outliers, maybe those are the types of observation that our model just doesn't understand, and it's very important to don't miss it, but keep track of them. Yeah, I can see the comment there about the data set, but sorry, it's a bit long comment, so I will answer this after the session if that's okay at the Q&A. Okay, so those are the two visualizations for checking how the model actually works, and if it's good or not. The third and the last visualization shows actually how what's the impact of each feature on our model, and this is very important, both from our perspective, but also from the perspective usually from executives that have to understand something in order to invest in it. So, like, no one wants to trust people that we don't understand, and that's the same with the modeling. So, if we are able to provide the information why model behaves like that, like the discussion is completely different story. So the first visualization shows the importance of feature, and this is very important, even as a different topic. So what affects our problem the most? So in this example, no, it was circle. So this visualization is not so impressive, because both of those features were extremely important. But we can see that the first feature was a bit more important than the second one. So if we would drop it, the RMS root mean square error of the model would increase around by 0.22, something like that. And the last visualization shows how each feature affects the model. So we can see on y-axis the average prediction of the model. On x-axis we can see the value of the feature. So for the feature x1, if the feature value is around -1, then the prediction value is around 0.65, and so on and so on. So we can see how the feature affects the actual predictions. And this is so important for explainability, from the explainability point of view. So like I can tell you the example from my work. So we worked on the model that would predict the ovarian stimulation results. So basically medical stuff. Yeah. So we want to know what clinical features affect the final outcome of our stimulation, and that was very important for the clinicians themselves. First of all, to understand what affects their job, basically. And second of all, if the model, if they saw that the model actually uses the same features that are being reported in the literature, and they saw that the impact of each feature is kind of the same or literally the same as it was reported in literature review, then they were like way more willing to use such tool for the automation stuff. So yeah, very useful stuff. Dalex, just use it. Don't ask, just use the package, because it is really great. Okay, so there are a couple of questions. Alex provide charts, something similar to Boruta when it comes to feature selection. Yeah, I mean, like basically the idea of Boruta is also Boruta also uses the permutation importance value, but Boruta uses by default the tree-based models. There's a package Boruta Shab in Python where you can change the regression, the random forest for the gradient boosted machine, but you know the idea is the same. Here you can just explain the feature importance using like any model that Dalex supports, which is a lot. Yeah, and are the feature importance values weights on neurons? I'm not sure if I understand the question correctly, but like definitely those feature importance value, like those are affected by the weights on neurons, because the weights on neurons affect our prediction, and our prediction affects this the behavior of this partial dependence profile. So yeah, it is definitely connected. Okay, so that was regression. I will speed up a little bit just to have more time for maybe Q&A or something like that. So the binary classification problem, again, we have a data set, like fake data set. Our input data will be like similar to a letter M in that sense, and our label will be a Z value here, also the color. So basically this part is 0 for the model, this part is, excuse me, 1, and this part is 1. The rest of our data set has a label 0. So this is classification tasks for us to solve. The same idea. So we split the data, we train the model, and we compile it. But in this time, when we are doing the classification task, make sure that the last activation function for binary classification is sigmoid function, because like the values from sigmoid are we can treat them. This is not the probability itself, but we can at least treat them as a probability and you know, use it as if it was. And from compilation, make sure that the loss is also correspondent for classification tasks. So as a default, for binary classification, it's binary cross entropy. Metrics, again, we don't want like mean squared error or mean absolute error there. We would rather use accuracy, for example, or area under curve. Optimizer stays the same. Adam is fine. Okay, and let's train the model. The fitting process looks the same. We'll use the callback here because we know how to use it, so it should save us some time. Okay, 7 seconds, and we are plotting the history. Model stopped the training right before the 30th iteration. Yeah, the accuracy skyrocketed from the initial model in 10 iterations, very close to 1 on both training and validation. And here definitely we could call it an overfit right here, because the accuracy, also the loss, is very close to 0. So those are extremely high values for accuracy. And in later iterations, we can clearly see that the training subset, like for training subset, the accuracy still increases. Not by much, because like there's not much to increase upon, but on a validation subset, it started to decrease. So definitely we started to overfit the model. But don't worry about that. We have early stopping, so we will restore the best weights. In this example, I'm pretty sure we will restore the weights from the 10th iteration, as it's the highest one. Yeah, so it should be around that. Okay, let's predict the value and compare the real label to our predictions. Here we can call it label because this is binary classification, so we would expect the data to have labels. In the meantime, I hope that everyone is still like up to the code right now, so no one is lost. If the tempo is too high, or maybe you would like to go back to previous examples and to clarify something, just please let me know in the chat. I have it opened all the time, so I will know to go back to give an example. Okay, so the real values, we know how it looks like. This is like for the test subset, so model didn't see those exact values in the training process. And this is the prediction. And model for most of the iterations were very correct. What's the funny thing here is the prediction values on the, let's say, edges between the label 1 and label 0. So, this is classification, but as I said, the last, if we use the sigmoid for last layer activation, we are kind of able to understand the predictions, so to treat them as a probability of. So in this case, probability of label 1. And on those edges, like, clearly it is hard to say where to actually cut the label 1 and label 0. So model also has a kind of problem with that. And for this, we can see that the probability values are also in range of like from 0 to 1. So this is the space where the model is not sure, and that's good. The model shouldn't be so sure about the label in this area. Yeah. Okay, so that was a binary classification. Let's go with multi-class classifications. And I think we will cover most of the use cases of Keras, at least for tabular data, of course, because we have also the video analysis, like text analysis, the image analysis, and so on and so forth. Okay, so for the multi-class classification, I've created a function that samples the data, like a given number of observations. In this example, 1,000 observations with 6 features. The noise ratio of those features will be around 20%, and this like 60% of those features, in this example, the 3 features basically, will be correlated with our prediction. We are not able to, of course, visualize all of the data. I will visualize how it looks feature by feature. But right now we will have a problem with more features, so it might be more interesting to solve it. Our label will look like that. So we have, if we are doing the multi-class classification in Keras, in R, make sure that our label will be a matrix of n classes. So in this example, we will have 4 class classifications. So our label will be will have 4 features, each of it indicating the label of observation. Yeah. So as I said, we can visualize the impact of features on our data. So we can see this is the first feature with the correspondence of y. So it's clearly kind of correlated, but there is some overlay here. We have 4 features that are correlated, and the rest of it are kind of noisy. This is just the distribution of y. So as you can see, percent-wise, it's the same. So each label has that. It's not unbalanced data. Basically, it's perfectly balanced. Okay, so we will again split our data and train our model. So what's different right now is the last layer again. Right now we have n-class classification, so 4-class classification. That's why we will have 4 units in our last layer, and each unit, each neuron will be correspondent to a different label. We will use the softmax activation function, which is like sigmoid, but for n-class classification. The idea is the same between the softmax and sigmoid. And for the loss and metrics, we won't use the binary cross entropy, but instead categorical cross entropy. Also not binary accuracy, but categorical accuracy. But the whole idea is the same. Like if you know how to train a simple deep learning model, you will know how to train the regression, the binary classification, multi-class classification. There are just like very few rules that you have to keep. Okay, so the model is compiled. We can train it. In the training process, make sure that for the training subset, you are not using any of the label in the trained dataset, and for the label, you are passing the matrix of those four labels. We can see in iterations that the model actually is quite good fitted to our data set. The accuracy right now is around 0.8, both on training and validation. So we didn't overfit the model yet. And we can predict the probabilities of the model. So maybe just to let you know. So the prediction of model looks basically like that. So it's also a matrix, and as I said, each feature is correspondent to our features from our classes. The values are values of the neurons that we have after the softmax function, and also we can treat each feature as a probability of. So this is a probability that the first observation is from first class, the second class, the third class, and the fourth class. So this is the predicted probability. To get the actual indices, so the actual predictions, we can use the function maxcall, and gives the index of the prediction there. So in this example, the first observation should correspond to a second label. So how much did the model misread our data? We can see that it had the most problems with the second and the third label, and from the error matrix, the prediction matrix, we can see that that was actually the case. Even though the model actually, the prediction itself was quite accurate, especially for the last and the first label. So that's how the multi-class classification works for in Keras. Okay, so we have a bit more time, so let's use it to explain, try to explain many different models at once with DALEX, and also to check if how the parameters of neural network may affect the training process. So again, I won't go through the details there. You can check it out yourself at home. So I've created some useful functions to run the prediction flawlessly and also to explain the models. But I will just very quickly say what they are doing, but not go through the whole code. So once again, we will sample the data set. This time for the regression task. Again, it will have this time 8 features with noise ratio of 0.5, and half of the features will be correlated, kind of correlated with our label, what we can see. The rest of the features will be very noisy. And this is a regression task. So in this example, let's see how the different combination of optimizers and activation functions like play the role with each other. So we will use, we will have like 3 different buckets. In each bucket 2 models. So first one will be optimizer Adam and stochastic gradient descent with ReLU activation functions. The last function will be always linear. So we have 2 hidden layers of ReLU and stochastic gradient descent and Adam. The second group will be again Adam and stochastic gradient descent, but the sigmoid activation function, which we told ourselves before that we shouldn't actually do, but I mean, let's see, maybe we are wrong. And the third bucket will be the same optimizers, again, the same number of units, but the activation function is tanh. So it's hyperbolic tangent. So let's define such models, let's split the data and train the models. So that's what the train model function actually does. So it goes through all of those parameters and trains 6 different models based on the parameters that we provided in this list. So in 16 seconds, we will have it. We will have those models trained. Okay, and let's see how the model looks like. So the first model had a loss 0.03, second one 0.06, 0.03, 0.4, so kind of higher. Again, 0.03, 0.05. Okay, so we can clearly see that the first model and the fourth model were the outlying values. So the first model fitted to our data perfectly. The fourth model was really far away from fitting to the data. Also, look at the range of the loss value, both on training and validation. So even for the training data set, the fourth model were around 0.4. On the training subset, the first model was way lower. Okay, so what was the third model? It was the SGD with sigmoid. So yeah, it actually makes sense. Slower optimizer, slower learning activation function. Yeah, that we should probably expect such behavior from that. Okay, so let's compare those models. The function explain models will go through all of those models that we've trained and create explainers for each of them. So this function may take a bit of time, but after those explainers will be trained, we will be able to visualize all of the models at one plot, which is like great for the comparison. So in the meantime, when those explainers will be trained, I would like to show you how it looks in RStudio. because I think that's one thing that's missing from Colab that I find really useful for applying the deep learning in R. So when we have we will have the data set, we create the model, we are compiling it. So up to this point, nothing changed, but the fitting is actually what makes the difference, because RStudio is kind of smart there, and it, as you can see, after each iteration, another dot is being visualized in the viewer. So you can basically track the whole training process of neural network in a real time, which is really great. Yeah. And also it's interactive, so you can check the values there. So yeah, RStudio still rules, still probably the go-to tool to use with R. Okay, so after 1 minute, explainers are being created. And as you can see, we can plot all of the explainers rated to a model performance value at a single plot. So what we can see, the first model, the fifth model, and the third model have by far the lowest values of residuals. As you may remember, those are the models that are using the Adam optimizer. So again, it might show that Adam is quicker to train, to be trained, to be fitted to the data. The third model, yeah, the residuals, the distribution is not what we would expect from a fitted model. This is the SGD combined with sigmoid. Again, SGD combined with hyperbolic tangent is the sixth model, and the second one is SGD with ReLU. So again, it kind of makes sense. ReLU should, the weights of the model with activation factor ReLU should be trained quicker. So that's why probably the model had lower residuals compared to those two. We can also visualize it using the box plot. So this is like the same distribution, but using different visualization technique. Okay, and yeah, that's hot. So we can also on a single visualization show the impact of each feature at the model. So from this visualization, we can see which feature were the most important and how they affected the RMSE after permutation. So clearly, model first, third, and fifth had the features first, second, fourth. Yeah, those are top 3 in each of this model. And after the permutations, we can see that the error would actually skyrocket if we would permute any of this feature. So at least the models interpret the data in the same way, basically. Yeah, this is another visualization. I won't go through that, but I think this is kind of interesting one. So it shows how the feature affected the prediction. So what were the prediction with a given value of a feature for each model? So like it's all that you would like to know when you are comparing the model. It's really great. So again, we can see the first model here, like barely visible, fifth one and third one. they interpret each feature the same way. So those were the best models. This is the sixth one, and the second one also interpret the first feature like in the same manner, but it's far away from understanding it to a best point. Yeah, and the fourth model like basically doesn't know what's happening. Like it's still strange data set for this model. Like that's why those residuals were extremely high. Yeah, so first feature, second feature, and the fourth one affected the most the prediction. And what we also can say here, so with the increased value of x1, the probabilities, the average probability of the model will decrease. Same for the x2, x4, the other way around. So increasing the value of feature should increase also the probability. Yeah, I mean, that would be actually it. I hope you enjoyed the session. We have 9 minutes left, but I think we can use it for the Q&A. Yeah, this is like a lot of stuff. I know that I sprinted through the code, but I just wanted to make sure that we covered all of the basic use cases, so the regression, classification, and multi-class classification. Deep learning is not that hard. I can promise you that. I'm sure that anyone that's interested in it will be able to understand and to run their own custom functions to solve issues with deep learning. Now, there are just a couple of parameters you have to keep track of, and after you will train a couple of different neural networks, you yourself will be able to assess what should be different in the architecture. Maybe we should use more neurons, less neurons, maybe higher learning rate, maybe lower, and so on and so forth. So the intuition comes with experience, I would say. Okay, I think that's, yeah, and I think that's it. So I will go through the questions that I didn't answer on the chat. Okay, so that there's a question: how can I make it run on multi-cores? As I can see on my local, it works on single core. Yeah, I think that's the case. So I won't guess because I'm not an expert in this area, because I didn't check on how many cores it runs on my engine. So sorry, I'm not sure how you could change this behavior. And there were a question regarding the data sets. Okay, so the data sets are pretty small. Yeah, I mean, they are pretty small for us to, not waste too much time for the training process. So that's why it's just like 1,000 of observations. Okay, I wonder if R has overcome problems with high-dimensional data that are composed of tens of thousands of features such as genomic data sets. Python is preferred to R when it comes to deep learning, which requires, okay. When it comes to this modeling, so the TensorFlow keras in R basically uses the TensorFlow background, the same TensorFlow background as Python. So that's I think that's very important to understand. So when you're installing the the packages, you will also install, as you can see, the reticulate. So when you are calling the keras and so on, the R also communicates with Python. Like the advantage here is that you can run the code from R directly with R script, and then also use the visualization technique built in in Python. But it also uses like the same TensorFlow as it uses in Python. Oh, thank you, Olgon. Yeah, I was kind of hoping that you will know the answer for that. Yeah, so you can check out the article that Olgon posted, how to use R on multi-cores. I'm sure that it's possible. Okay, so the question, thank you for the talk. Yeah, my pleasure. My question, how we could decide on the best hyperparameters. As I mentioned, there are many hyperparameters, number of layers, activation. Yeah, we know there are many parameters. That's true. You showed example of comparison of different Keras models, but grid search might be an option. Do you suggest grid search? Yeah, sure. Surely you don't want to specify the actual value that you want to check out, because still the whole process of choosing the best hyperparameters is like there's no like golden rule for every data set to choose the best architectures. So you will most probably check many different iterations, like a different number of neurons, layers, and so on. So grid search, yeah, of course, might be an option. You can also check out like the tensor board, for example, but in the Python version, the tensor board. The trick is to use the proper space for finding the proper parameters. Because, you know, we could set the number of neurons, I don't know, from 1 to 10,000, whatever. Why not? We have time, let's compute that. But for our custom problems, we will most probably know how much neurons, how much layers, and so on will be a proper value for solving the task. So, for example, lately I was training a deep learning model on the data set with less than 10 features, or it was 10, like around 10 features. Like the data set was composed of medical data, around 10,000 of observations. So I ran grid search with 1 hidden layer, 2 hidden layers, and 3 hidden layers. So not that much. Like this is not like a huge architecture. And from our observations, after the like I don't know, thousands of iterations, because we had the time, so we checked many different options. Clearly, the best architectures were the ones with 2 hidden layers, and 3 hidden layers were way worse than just 1. So, you know, just to bear in mind, like more is not always better in this case. Like that's not how the deep learning works. More layers means more complex architecture, and complex architecture are harder to train. No, because this is complex. So there are a lot of areas where the training process can go wrong. and probably will go wrong. So don't no. Keep it simple. If not needed, keep it simple. Changing the architectures for very complex one should be because of some reason, I would say. Okay, all right. So I can see no more question, and we are about the time. So it's 6:30.
Yeah.
If you will have,
go ahead. Sorry.
Yeah, I'll go. I wanted to ask you if you have some final speech prepared, or
Yeah,
I should close it out.
That's okay. So yeah. Let's wrap it up maybe. So yeah, I cannot see more questions on the chat. Thank you so much, Krystian. It was a pleasure to have you here, and thanks a lot for this great talk, and it was very valuable. You provided very fruitful and important information, like from A to Z, like you took things very simple, step by step. So thank you so much for that. Thank you for your time. And so yeah, it's 6:30 in Europe right now, and in Turkey it's 7:30, but still we have around 100 people, and so that's I think amazing considering today is Friday. So people prefer to stay here with us instead of going to have some party. That's really cool. All right, so yeah, this was like very dense day, and then I think I mean very nice. We had very nice talks today. So thank you so much all for joining us. So please don't forget to join tomorrow's and Sunday sessions. Tomorrow and Sunday also very cool agenda is waiting for you with also very exciting talks and very exciting sessions. Hopefully we will see you tomorrow. Oh, Krystian, somebody texted in Polish to you.
Oh,
yeah.
Thank you. Yeah, guys, thank you very much. Thank you all for tuning in. It was a real pleasure.
Perfect. Okay, so then I think we can slowly wrap it up. And thanks a lot, everybody, once again. Thanks a lot, Krystian, once again. And see you soon. Bye-bye.